So to understand significant figures, I think it's helpful to understand why we have them. And so for this, I'll give a little story that kind of will help you maybe appreciate the significance or reason as to why we use significant figures in science. And the story is this, back in the 1800s, an engineering group was tasked with determining the height of Mount Everest. And when they did that, using their tools and a lot of time it took to get the height measured, they determined the height of Mount Everest to be 29,000 feet exactly. Well, when a country and a government pays the engineering personnel to measure this height and they come back with 29,000 feet, that doesn't sound like it's very accurate. It sounds like they almost stood at the base and looked up and said, meh, that looks like it's 29,000 feet. So the engineers, instead of telling the government that they measured the height to be 29,000 feet, they said it was 29,002. And all of a sudden, it sounds like a much more accurate measurement of the height of the mountain. And so this forms the basis of our understanding of significant figures. When we look at 29,000 feet exactly, it was an exact measurement, although it looks like a rounded number. And so we need to understand what significant figures are. And to understand significant figures, we have to understand significant digits. And the reason we have this is to accurately convey how precise our measurement is, so that when we give a number like 29,000 feet, and it's exactly 29,000 feet, that we can convey that information of how accurate that measurement is. And so we wanted significant figures then as a way for us to tell what we do know from a measurement and what we do not know from a measurement. Notice they didn't report 29,002.7358 feet. Notice they didn't know the 0.7358 part, so they didn't report it. They just reported what they measured it to. So let's determine the number of significant digits in some of these values we've just discussed. So I have 29,000 feet, and that's where it's about 29,000 feet, i.e. you stood at the bottom of the mountain, looked up and said, it's about 29,000 feet. The next number is 29,000 feet exactly, and then the last one is the 29,002, which sounds more precise than the first two, even though necessarily it may not be. So in the first one is to determine the number of significant digits. We have a rule we need to follow, and that is this. The first rule about significant digits is that all digits except 0 are significant in the number. So therefore what that means is, notice 29,000 has 5 digits. The 2 and the 9 are significant. That's also true in the second 29,000 number, because again those aren't zeros. And in the third number we have here, the 2, the 9, and the 2 are all significant. And so the first number has minimally at least we've underlined 2 significant digits. In the second number we have 2 significant digits underlined, and then the third number we have 3 significant digits. Zeros between non-zero digits are significant. So in our example here, the first one, we have zeros, but they're not between non-zero digits. There's a 2 and a 9 on the left, but there's no other digit on the right of those zeros, so those aren't necessarily significant. Same with the second one. But in the third example, notice these 2 zeros fall between 2 non-zero digits. They fall between the 2 and the 9 on the left and the 2 on the right. So those are significant in the third number. And the final rule for these numbers that are greater than 1, like these we have here, numbers around 29,000 are much greater than 1. So here's the rules we use. If a decimal point is shown in the number, all digits are significant, including the zeros. So in this regard, what should have been done by the engineering people is to put a decimal point after the number to indicate that all the digits are significant, that it was exactly 29,000. And so in this regard, these three become significant because that decimal point is there. If the number doesn't have a decimal point, like the first number, then all the zeros to the right of the non-zero digits are not significant. And so in that first 29,000 number where we estimated the height of the mountain was 29,000 feet, we stood back on the ground and said, oh, it's about 29,000 feet. Those would not be significant values. They are just holding the place of the size of the number. In this case, 29,000. And so the number of significant digits for each of these each of these numbers is, for the first one, it is 2. Whoops. It is 2. We underline two numbers. The second one is 5, and the third one is 5. And notice the last two numbers are way more significant digits than the first one, because those two values are more precise. Those were more precise measurements. We use better tools to get those precise measurements as opposed to just standing at the bottom of the mountain with no tools, just looking up and guessing as to the height of the mountain. Now, let's go through a couple of examples that will really kind of bring all this home for you. So give these a try. Try to determine the number of significant figures in each of these values using some of the rules we just talked about. Pause the video now and then restart it when you think you have the answers, and I'll walk through each of the solutions. So each of these are greater than 1, so all the rules on the previous discussion when we talked about rules apply. And so one of the first rules was all non-zero digits are significant. And so I'll underline all the significant digits based on that rule. The second rule was any zero between two non-zero digits are significant. So the 0 on this first one between the 2 and the 2. The 0 on the second one between the 2 and the 2. The 0 on the third one between the 5 and the 2. The fourth one down, there's no non-zero digit to the right of those zeros, so I can't underline anything there, and the same with the last one. The next rule, the third rule, was if you see a decimal point, all the digits are significant. So that makes this kind of takes out a few of these for us. The first one doesn't have a decimal point, so we leave it alone. The second one has a decimal point, so I can underline that last 0 sitting next to the decimal point. The third one down, we've already underlined everything. The fourth one down doesn't have a decimal point, and the fifth one down does have a decimal point, and so we can underline those 3 zeros. The last one was underline, if it doesn't have a decimal point, all the zeros to the right of the last non-digit non-zero digit is not significant. So this is a not significant one. So the first one, that 0 is to the right of the 2's, and so that one is not significant, so I will not underline it. And the same rule applies for the fourth one down, the 0, 0, 0 that you see there next to the 4. There's no decimal point and there's no other digit there, and so that stays as is. And so if we determine the number of significant figures based on these numbers we have 3 in the first one, we have 4 in the second one, we have 6 in the third one, 1 in the fourth one, and we have 7 in the last one. Okay, but what about numbers that are less than 1, not less than 0? There we go, I updated that for you. So now in numbers less than 1, so previously we were doing numbers greater than 1, so in numbers less than 1, Now all these numbers will pretty much have a decimal point, so we can't use that decimal point rule at all. So numbers less than 1, all zeros to the left of the first non-zero digit are not significant. So here's two examples I have here. Let's go through those again like we've done before, and let's start with our first rule, which was any non-zero digit is significant. So on the first number I can underline those 3, and on the second number I can underline those 2. The second rule was if there's a 0 between non-zero digits, those are significant. I don't have any zeros in between, and so that doesn't count. Step 3, or rule 3, has to do with numbers greater than 1, so that doesn't count for these. These are all less than 1. They're all decimals. And the fourth rule is this one, is the numbers to the left, the zeros to the left of the first non-zero digit are not significant. And so here we see to the left of the 4, there's 2 zeros, so those are not significant. And on the second number, notice I have 0, 0, 0, those are not significant. The 3 is significant, the 2 is significant, and every other 0 after that is also going to be significant, and so anything to the right of those digits is significant, or in between. So in between, which is rule 2, or to the right, are all significant. Let me give you a couple to try. So here's a couple to try. Go ahead and pause the video. When you're done, come on back and I'll walk through these 4 examples. So on the first one there, so using our first rule, on the first one, the 1, the 3, and the 1 are all non-digit, or non-zero digits, so they are all significant. On rule 2, any 0 between them is also significant. And then the third rule doesn't count because these are all less than 1. And the fourth rule, the first 0 there is not significant, but the last 0 is significant. So because any 0 to the right of the non-zero digits are significant in these values. So in this case, the first one would have 5. In the second one, we can see the non-zero digit there, that 4. The second rule doesn't apply. There is no 0 in between 2 non-zero digits. And then all the zeros prior to the 4, to the left of the 4, are not significant. And there's no other number to the right of that 4, and so that would only be 1. In the fourth number, again, the 2 1s are significant. The 2 zeros to the left of those 1s, as in rule 4, are not significant. And the rest of the zeros are significant because they could have easily been dropped in the number. If they were not, if you were, like, for instance, recording that number and those 3 zeros shown here were not significant, like you were estimating from the bottom of the mountain, so to speak, you would have recorded that number as 0.011 and left those 3 off. It wouldn't have changed the value of the number. So, and the fourth one, again, those 3 digits are significant as defined by rule 1, rule 2. Those 3 are significant, and then the first 0 is not significant. Sorry, on that third number, that was 5, and on the last number, that's 1, 2, 3, 4, 5, 6 significant figures. The last thing I need to talk about is scientific notation. What if the number is in scientific notation? If it is, significant figures is really easy. You'll love it. So let's take a number that we had previously. Let's take 29,000, and this is 29,000 without the decimal point. So this is the estimate one. If we were to convert that to scientific notation, to do that, what we would do is, if you remember, I'm not going to go through this deeply because that's not really part of the video, but the decimal point should have been there if we would have put it in. If I move it over 1, 2, 3, 4 spots there to here, so let's see, 3, 4 spots to there, it would become 2.9, because the decimal point would be between the 2 and the 9 because I moved the decimal point over 4 spots, times 10 to the 4th. The fourth meaning I moved over 4 spots. Notice because those 3 zeros are not significant, I don't put them in the value. I don't put them in the scientific notation. If I have the exact, if I have the exact 29,000 value, it means we did engineering and we measured it exactly. The decimal point would originally be there. I can move that over 4 spots, just like I did on the previous one. But in this case, because those 3 zeros are significant, it would be that value. And notice number of significant figures for each of these. The first one would have 2 because it has those 2 numbers, so that would equal 2 significant numbers. And on the next one, there's a number, it's greater than 1. Using rule 1, those 2 are significant, the 2 and the 9, because they're non-zero digits. Rule 2, there's no 0 that falls into that category. Rule 3, because this is a number greater than 1, all the digits are significant because there's a decimal point showing. And so notice here I get 5, which is exactly the result we got when we previously analyzed it. So notice when you have scientific notation, here's the cool part. You just look at that number, whether it be this number or this number, and you just count them up. You don't have to worry about zeros, where they are and all that, because it'll all take care of itself by writing it in scientific notation. In fact, if you like scientific notation, if you write the number in scientific notation, it gives you the number of significant figures. Let's do a couple of examples. So here's a couple of 3 examples of numbers in scientific notation. Notice I can tell it's in scientific notation because I see that times 10 to the some power. In this case, on the first example, it's 10 to the third. On the second one, it's 10 to the negative 7. On the third one, it's 10 to the negative 10th. You don't care if it's negative 10th, negative 7th, or positive 3. It's in scientific notation. When it's in scientific notation, all you have to do is look at the number before the times 10 to the whatever, and you just go 1, 2, 3, 4. So the first one is 4. You just count them all. And the second one is 1, 2, 3, 4, and it's 4. And the third one is 1, 2, 3, 4, 5, 6, 7, and it's 7. So all you have to do is count the number of digits in that number, and it's already, all of those are significant. That's one of the powers of scientific notation. It automatically gives you the number of significant figures. So you can take any number and convert it into scientific notation, and then just count the digits if you're comfortable doing that. Some people are not, and so they'd rather do some of the things we did previously. For the last thing, here's a couple 5 to try on your own, a mixture of all the different types we talked about, numbers greater than 1, numbers less than 1, and significant figures, all wrapped up into one worksheet. So give it a try. You can pause the video, come on back, and I'll walk through the 5 examples and kind of walk through the proper answer. So in the first one, we have a 1, a 3, and a 1. Those, based on rule number 1, those are all non-zero digits. These 2 zeros in between them are also significant, and because we see a decimal point, that one is also significant. So in this case, we have 6 significant digits. In the second one, scientific notation, love that. That means all 3 of those digits are significant, and so we would have 3. Third one, it's a number. I see a 2, 8. There's not even a 0 in this value, and so that's a nice one too. It's just 2. In the fourth one down, we have a number less than 1. I know from rule 1, the 7 and 7 are both significant. The 0 in between them is significant based on rule number 2. And then all the zeros to the left of that first 7 are not significant based on rule 4. And so that would be a 3. And then the last one, again, scientific notation again. If it's scientific notation, I don't even think about where the zeros are. Every digit I see, I count up, and we get a 4 for that one.